Hi everybody, welcome to lab number 7 of GG497 Geological Visualization. This week we're going to South Wales where we'll examine the Newport Map. And I've selected the Newport Map because it's a really nice introduction to folded rocks. If you look at the Newport Map that we've turned on the side here, hopefully you're struck by this almost symmetrical repetition of colours in the eastern side of the map that form these strip-like exposures. And if you look at the colour pattern of different rock types, you can see that right in the middle of that line of symmetry are these blues and purples. Then that grades out into I guess a mauve sort of colour, thin bands of orange, and then pink. And you can see that there's that symmetry almost in the strip exposures. Okay, that sort of exposure pattern you remember from the lab is very characteristic of folds, where one limb of the fold shows you the stratigraphy, and then as you cross that limb of the fold over the hinge of the fold, you see the mirror image of that stratigraphy. So we've got this nice fold that's caused by Silurian rocks, and the limbs, I guess, are most well defined by these old red sandstone, these Devonian rocks. So we have this fold that, as well as forming these strip-like exposures, the exposures seem to close and bend round, so that indicates that our fold is plunging. But then as we move towards the west of our fold hinge zone, we see that the outcrop patterns change to be more sort of bullseye, more parallel to the ground contours, which indicates that the dip of this limb of the fold, it flattens out, it tends to shallow, to become more horizontal. So we have a fold axis with a dipping limb, and that dipping limb, the dip of that limb decreases so that the rocks flatten out. So that's the general structure, folded rocks with variable dips. There are a couple of angular unconformities within these rocks, most notably between all of the oldest material and then the Triassic and Jurassic rocks. But that introduction should give you everything that you need to start answering the question. So as ever, one of these labs will have a question sheet that asks you to evaluate certain statements, to measure things, and to understand the geometry of the fold. And then there's a hill profile already drawn for you, where you can add in your interpretation for the cross section through the area. Okay, so in the next part of the video I'll talk you through how I would approach this cross section, and then we can see how you get on. Okay, thanks guys, I'll see you in the next part. Hi everybody, welcome to the next in our series of geological cross-section drawing. Today we're looking at the solid geology sheet for Newport, published 1975. And what I thought I'd do is explain some of the things that are going on with this map. Probably the most striking feature of the Newport sheet are these repetitions of Devonian strata which form these strip-like exposure patterns. And if you look at the colours and the symbols for some of these strips, for instance looking at this pink rock on our map, you can see that it's the same rock type. This pink rock that's forming this strip-like feature is C1, which on our geological column is part of the St. Morgan's group of the Devonian strata. And on that's this strip here, and then on the other side of this darker purple unit we see it crop out again. We've got this repetition, or symmetry if you prefer, of the stratigraphy. Now if you look closely at the map, you should see that there are dips within these rocks, where in general on this side of our line of symmetry they're dipping towards the southeast in this direction. And then on the western side of that line of symmetry, the rocks are dipping towards the northwest. So we have this alternate position of dips towards the southeast on this side of our line of symmetry, and then towards the northwest on this line, to the west of the line of symmetry. So what we've got is really good evidence that we have a folded sequence of rocks, where one limb of the fold, it's dipping down towards the southeast, and then as we move this way we cross the hinge zone, and then as we cross the hinge going towards the northwest, the rocks dip in that direction. So we have this anti-formal fold in this part of the map area. And the rocks in the core of that anti-formal fold, right in the middle of that anti-formal fold, are Silurian. They're Silurian limestones which predate the Devonian stratigraphy. So we have the oldest rocks in the middle of our antiform, so it's also an anticline. It's an antiformal anticline. Now as we go up through the stratigraphy, after our conformable sequence of Silurian beds and Devonian beds, there's an unconformable horizon between the Devonian and the Carboniferous rocks. So in this case, the oldest rocks of the Carboniferous in the Newport area belong to the Carboniferous limestones, which form these relatively thin strips in this orientation. And then above those Carboniferous limestones there's another unconformity, a gap in geological time with net erosion. And on top of that unconformity we have the coal measures and millstone grit being deposited. Now we saw the millstone grit in our previous example, and these are the same rocks just in the Newport area. Now again, after deposition of the Carboniferous there was another unconformity, and on top of that unconformable surface the youngest rocks of the area, the Triassic and Jurassic rocks, were deposited. So we could imagine if we could skim off that surface of Triassic rocks, if we could take those Triassic rocks away from this region of the map, if we were to drill down through the subsurface, we'd probably end back into the Carboniferous coal measures, and then if we drilled further into the Carboniferous limestones, and further still into the Devonian and Silurian strata. So that's the general structure of the map. We have this fold here, and as we go this way the angle of dip of this limb flattens out, So much so that we're back to the horizontal outcrop patterns where the geological contacts are parallel to the ground contours. So we've got this relatively steep dip on the limbs of the fold closest to the hinge, but then as we move away from the hinge in the northwest direction, that dip evens out gradually. So it's a nice concentric fold where we go up towards the hinge here, we come down on this side of the hinge, and then we flatten out as we head to the northwest. Now, aside from that ductile deformation which has given us these folds, you can see that this map, particularly in the coal measures, is absolutely riddled with faults. Most of them have very little displacement. So in here, for example, there's not much difficulty for many of the faults in following one bed across the fault onto the other side of the fault. But then there are one or two faults which do have a sizable displacement. For example, the largest one that I can see just from scanning the map is this Coidipine fault, which has displaced some of the beds of Silurian limestone, something on the scale of 1 to 2 kilometers. Okay, so to summarize that, then we have these folded sequence of Silurian, Devonian and Carboniferous limestone rocks, Carboniferous age rocks, which have been folded. There's a few unconformities within that sequence, and then sometime after the folding, those rocks have then been faulted by this dominant northwest-southeast set of faults, but then there also looks like there are a few that are subparallel in the northeast-southwest orientation. So what I've done now is put on our tapes to show the two ends of our cross section. So the coordinate for this part of this end of the cross section is 340,900, and this part of the cross section is 250,970. And what we're going to do is draw a cross section along that line between these 2 points, and imagine if we could look side on what the geology would look like in the subsurface. Now obviously this is going to be the hardest cross section that we've done to date, so I expect it, and I expect us both to take a fair bit of time over this. But I reckon we've got an idea of what's going on, so we should probably get drawing. So here we are zoomed in on the area in which we want to draw a cross section through. Here are my corners of the tape to mark the ends of the cross section. And unlike the other cross sections that we've done so far, there's a fair bit of information that we should collect on this cross section. We're going to start in the usual way. We're going to mark on the geological contacts, but then we're going to take a minute to have a look if there's any other information we need to get hold of. So I guess I'll start with having my cross section strip put on the right places. I'm going to mark my extremities of the cross section with A and B, and then I'm just going to go along and mark on my geological contacts. So there's the border of a sandstone within that St. Morgan's group. There's the boundary with the underlying Raglan Marl group. And I've got another sandstone here. And then what I'm going to do, I'm into the Carboniferous, the Carboniferous stratigraphy, and you can see there's a whole lot of these very thin limestone bands. So what I'm going to do is just mark on, that's the end of my Upper Devonian, and then that's the start of my Carboniferous limestone. Then the Carboniferous limestone stops there. Then on top of that I'm into my Millstone Grit series, so I'll go to there with my Millstone Grit. And then I'm into the coal measures, so I've got the one bed of the coal measures there, the lower pennant measures, and then I'm into quite a large sandstone that marks the youngest bit of our stratigraphy that we can see. So then what I can do to make myself feel a little better that I'm making progress, I can draw on a thin veneer at the appropriate colour. So this is my intervening sandstone, relatively thin bed of it. Then my Raglan Marl group of the Devonian. Then I've got some of my coal measures. That's a sort of yellow. That can, the lowest part of my measures, the coal measures can be green. Then we've got some of that Millstone Grit, which I think in the other maps we've coloured in as a grey. Then my Carboniferous limestone, so I'm going to pop those as a light blue. And then for the uppermost bits of the Devonian, I'll put them in as this brown. Okay, so there's my colours to show what if you were to walk along this transect, what rock types you'd have, and then I'm just going to give them their labels so they correspond to something in the key. So all of this is rather confusingly, this all belongs to C1, but I'm going to give it its name of, this is the RM, the Raglan Marls, this is the St. Morgan's, so is this. Here's an intervening sandstone, SST, SST. Then what I'm into, let's call these my Upper Devonian, Upper Devonian. Then I've got my Carboniferous limestones. Then I'm into my Millstone Grit, and then from then onwards I'm into the coal measures. Okay, great. Now what I need to do is plot some of the structural information, and this is, it looks deceptively easy, but there's very many ways to go wrong with this. And if we move our cross-section panel away, you can see that there's some degree of variation of dip within our folded region. Now my advice for this sort of cross-section where you have some dips which can confuse things slightly is to look at an area and take what you feel to be the most representative. So for example, in this region, all of the beds, or the majority of the dips I can see, are about 20, 28, 12, 30, 25, all dipping towards the southeast. If you were to look closer though, you can see that very occasionally there's one that dips at 10 and 10 going in the other direction. But the dominant story for this part of our sequence here seems to be based on the data that we've got on the map and the general outcrop patterns of the rocks.
the dominant dip seems to be about, say, 25 degrees down towards the southeast. So even though I could get a little bit confused about stuff in here if I looked at every single data point, for this part of the map, using my understanding as a geologist, I'm going to say that these boundaries in this region, they're all dipping at 25 degrees. Okay? Now, what I need to do as I move across through the stratigraphy going in this direction, I need to be aware that those dips are going to change, because we're going from one limb of the fault over the hinge onto the other limb of the fault. Sorry, not the fault. We're on one limb of the fault here, and as we go over the hinge, we're going onto the other limb. So we're going to expect the dips to change direction, maybe change angle as well. And indeed, as we travel over the hinge, which is probably in somewhere in this direction, we can see that the dips of the fault are about 18 here, 30, 10, 20. All of that hovering around sort of like somewhere, if we were to take a median, somewhere in the 20s. And I can't really see any other dips that are giving me conflicting information that are going the other way, nor can I see a systematic trend to indicate that in this particular region it's starting to flatten. All I can see is that these beds and these contacts in this region are all dipping in that direction of about 25 degrees also. Okay, now as we continue though, we start getting 20-degree dips here. You can see one there right on the line of our section. But then as we travel into our coal measures, we're starting to get dips very, very low angle. For instance, here's 8 degrees. Just off our cross section there's 5. There's 6 degrees. Looking at the outcrop patterns, they look more or less flat. So what I'm suggesting is happening is as we go this way, this 20-degree dip, this moderately steepish dip of 25 degrees, I think that it's beginning to flatten. At least that's what the map is telling me. So then what I'm going to say is that these rocks, these coal measures rocks, they've got a dip, let's take 5 degrees. So these from here, this boundary certainly is dipping at 5 degrees, and as is this one. Okay, that's become slightly confused on my cross section, because this map it requires more information to be recorded. But on this now, what I've got is the location of the rock types on the surface along my cross section between A and B. And I've also got some key structural measurements telling me about the angle of dip of the rocks. We don't go through any faults along this section, we'll save that for another time. So what I think we can do now is go and take this data and start plotting our cross section. Okay, so here's our cross section line and our hill profile between 250,970 and 340,900, points A and B on our cross section. So now what I can do is take my the stuff that I've recorded for my cross section line, and I can put it on my hill profile. Now again, through reproduction, those points A and B are a couple of mil either side off, but that's okay. I can accept that. That's just the way it goes, I think. So if I just line it up with A and then just kind of amend this slightly, so that I'm on B there. All I've really done is cut off a little bit of the St. Morgan's group, which I think I can be forgiven for. Okay, so now what I'm going to do is go along my section and mark on at the base of the section where those geological contacts are. Okay? And what I'm going to do then is mark on where those geological contacts would hit the hill profile. And to do that, I put my protractor, the crosshair of my protractor, on that little mark, and then I mark at 90 degrees, line those 2 points up, and there is one contact. Just next to it is another one there. And then as we go further over along our cross section, we've got another one. We've got another one there. If you want to use a protractor for everyone, I'd recommend that, because for the sake of expediency, I'm trying to speed this up a little bit. So that was that middle one. There's another one there. There's another one there. And then we've just got these two more to do. That's vertically up there. And that's vertically up there. So those are the points, if we were to walk along this cross section, along this hill profile, these are the points at which we'd see these different rocks. So now what we can do is, using our cross-section strip as a guide, we can paint that very thin veneer on the surface, and it should be really, really thin for this cross-section, because in a minute we're going to add some stuff down on the base of the cross-section underneath the surface. That's my St. Morgan group. That's my sandstone. Then I've got my Raglan Marls in the middle of my fold. And then as we go this way, somewhat complicated set of colours. We've got our browns, which are our uppermost Devonian rocks, and we've got our Carboniferous limestones. Then we're into our millstone grits, and then we're into our Carboniferous coal measures. Let me get the yellow. Where's the green gone? There. So at least we know what rock types we'd walk across along the surface, even if we can't plot them at depth yet. We know that that's what we see at the surface. Okay, now we have to ask ourselves, if we're plotting these rocks dipping in the subsurface, do we need to change their dips to take into account any strange orientation of our cross section? Remember, if our cross section line on our map is anything other than perpendicular to the strike of the beds, then we should modify the angle of dip that we record to be an apparent dip. Because if we were to take a cross section at any angle other than perpendicular to strike, the beds would appear to have a lower angle of dip than they actually do. We call that phenomena apparent dip. And we did an exercise using a block diagram, which I'll show you now, that shows what I mean by apparent dip. Luckily in our case, this line of section that I've selected is pretty much perpendicular to the strike of the beds. In general, the beds are kind of striking in this orientation, and along the line of our section we're taking a line that's perpendicular to that. So we don't have to modify the dip of our beds for our cross section. We don't have to calculate an apparent dip. We've drawn our cross section line at the appropriate angle to avoid that. So that's a bit of good news. So what that means is that we can just take the angles of dip, the true dip of the beds, and plot them at that correct angle. Okay, now this next bit is going to require me to make some mistakes and then rub them out. So it's always handy to have one of these pencils that's got a rubber on the end. So, let's start with the easy part of our cross section first. Let's go to this intervening sandstone bed that's dipping at 25 degrees towards the southeast. So I've marked 25 degrees with my protractor, and I'm joining up the contact on the surface along that 25 degrees. I can do the same for the next angle at 25 degrees. Let's plot that one there and link those two up. So I've plotted my sandstone bed. Then as we go in this direction, I've got this angle of my angle of dip here for these rocks, these first couple of contacts as being 25 degrees, pointing the other way towards the northwest. So horizontal 0, 10, 20, 25. Now this is the bit where I know later on I'm going to have to rub this out, and you'll see why in a minute. So that's one contact at 25. There's the next contact at 25. Okay, so I've got my sandstone bed that's sort of defining this fold for me at the moment. Okay, now we're going to run into a little bit of a problem. If I were to continue drawing these beds at 25 degrees, we're going to quickly run into a problem. Let's put this next one in at 25 degrees and this one in at 25 degrees and this one in at 25 degrees. Now we're getting to the point where our beds, according to our map, those boundaries are, instead of dipping at 25 degrees, these beds are now dipping at 5 degrees. So plotting that at 0, take that to 505. It's a very, very modest dip. And this one next to it. Okay, so the problem that we've now got is by drawing these beds at 25 degrees and drawing these beds at 5 degrees, can you see that our millstone grit at one part of its thickness has a maximum thickness of this distance here, but then it fans out dramatically, it thickens by at least 300% just a kilometre away, and generally sedimentary rocks don't do this. Okay? Generally sedimentary rocks across their entire length of deposition, they tend to be more or less a constant thickness. We certainly don't see thickness changes like this in reality. Okay, so what we have to do is modify our cross section so that these beds make sense, so that we can avoid this ridiculous change in thickness of different sedimentary beds. Okay, so what we're going to have to do then is look at this point where we've got our 5 degrees, and what we've done there is taken real data from the map. So whichever geologist mapped this, he or she was confident that those beds there are dipping at 5 degrees, and I see absolutely no reason to doubt them. So what I'm going to do is put my protractor rather, so the crosshair is on that tick mark. Okay, and mark on a perpendicular point to it. So that tick mark is along the bedding plane that I've drawn at 5 degrees, and the crosshair of the protractor is on that tick mark, and I've just marked on a point perpendicular to it. Then what I'm going to do is draw a line, which I'm going to rub out later, along that point. Now let's turn back to the map and try and understand why I've drawn that line. If we look at the orientation of the contacts of all of our geological units, can you see that they're all oriented in the same direction? They're more or less parallel to each other, aren't they? Like even the contacts within the older Devonian rocks, they're parallel, or more or less parallel, to the contacts within the Carboniferous rocks. It looks like, even though there's gaps in geological time, there's unconformities within that sequence, they look like they're paraconformities because the rocks seem to have been laid on top of each other and then tilted to give us this sort of parallel nature of the contact. So if the rocks here are dipping at about 5 degrees in that direction, then if we were to drill all the way down perpendicular to those bedding planes, all of the layers beneath them along that length perpendicular to the bedding plane would also be dipping at 5 degrees. Okay, so that's what I've tried to draw here. At the surface, our geologist friend mapped the contact at 5 degrees. And because of the outcrop patterns, we can infer that these rocks are parallel to each other. And if we were to drill down into the surface, perpendicular to those bedding planes, all of the subsequent bedding planes that we would cross would also be dipping at 5 degrees. So what we can do is pick up our protractor and put the crosshair of the protractor along that line at the intersection of the bedding planes that we've currently drawn at 25 degrees. So let's get our first one in. Then let's mark him on at 5 degrees. There we go. I get that lined up. And we can plot that then at 5 degrees. Then if we do the next one, there's the intersection. It's quite hard to do this if you're looking for a frame of reference of where the horizontal is. There we go, that's another 5 degrees. Then that one, if I eyeball it, that's another 5 degrees. And then if I eyeball this one, yeah, that's about 5 degrees. And that one is about 5 degrees. Okay? Then what I can do is remove the lines that I no longer need. So no longer need. If I take this sandstone that's dipping in this direction. Over here it's dipping at 25 degrees, but then over towards 250970, its dip flattens to become 5 degrees. So I can get rid of the bedding plane that I had originally drawn. So that now I have a more realistic bedding plane that follows or agrees with our angles of dip that we've measured on the surface. So here's, don't need these bedding planes anymore. They've been superseded. That's good. Don't need that one anymore either. Okay, so now hopefully what you can see, we're kind of getting towards the point at which where we're being true to the map. We're being true to the geologist that found the rocks here dip at 25 degrees and the rocks dip here at 5 degrees. And what we've been able to do is show how that bedding has changed. Its angle of dip has changed, but we've been able to maintain a realistic and constant thickness. We haven't got sedimentary rocks which like explode and get really wide or shrink down into a point. Instead, we've got these rocks that are more or less a continuous thickness, which is what we observe in geology. Okay, so now what we can do then is rub out the bits we don't need. We no longer need this guideline. We've got everything that we need out of it, which it's given us our orientation. And now what we can do is start drawing on or colouring in some of our geology to make it feel like we've made progress. Now this method of drawing a cross-section so that you maintain the constant thickness of sedimentary beds is called the Kink band method. So named because you form your cross-section by kinking every time you get a change in dip. And you can imagine that if you had a cross-section where you had a number of different changes in dip along that cross-section, you can imagine that that would look, for want of a better word, very kinky. For us, we've only got this one change in angle of dip because it's a relatively simple example. So we've just got the one kink in our cross-section. So now I'm drawing some more of the pennant measures, and then beneath that, what have I got? My millstone grit, obviously, beneath the core measures. And then underneath that, I've got my whole group of Carboniferous limestones. Under which there's the Upper Devonian, and then under that we're into the St. Morgan's group, which I've been colouring in pink. Right. Then there's this little sandstone bed. And then I'm going to leave it there for a minute because we need to think a little bit about what we're going to do next. Okay, in the core of our antiform, at least along our section, the lowest unit we can see is the Raglan-Marl group. However, if we were to look back at the map, you can see in the far northeast the oldest rocks in the area forming the core of our antiform. There are Silurian limestones. So somewhere in this fold underneath these rocks we're going to run into some Silurian limestones. Now it's relatively straightforward to calculate where we could expect to find these Silurian limestones, and the way that we do that is to look at our stratigraphic column and figure out the thickness of this Raglan-Marl group, how thick it would look on our cross section, and how we could then interpret where the Silurian limestones would fall. Now you can do that precisely using a calculator, but for sake of expediency of this video, I'm going to look at the column and compare the thickness of the Raglan-Marl group with the St. Morgan's group. And what I can see is that the Raglan-Marl group is just about the same thickness as the St. Morgan's group. So the Raglan-Marl group is about the same thickness as from there to there on our cross section. So from there to there on our cross section has a thickness of something like 2.5 centimeters. So I'm going to draw a series of points that are 2.5 centimeters perpendicular from its upper contact, so 2.5 centimeters, like so. Two and a half centimeters, 2.5 centimeters. And then what I'm going to do is very faintly draw an interpreted bedding plane like so. So maintaining a constant and realistic stratigraphic thickness, I've interpreted this to be the approximate or interpreted position of those Silurian rocks that would exist beneath our Devonian rocks. Okay, so I'll just dash that in to show that I'm, not 100%. I know they're going to be down there somewhere, but what I've done here is a little bit of calculation, a little bit of common sense, and a little bit of geologist energy. And now what I'm able to do then is to finish the colouring for the Raglan Marl group. Sorry, I appreciate that when I do this it makes the camera wobble somewhat, but when needs must. So that's our Raglan Marl group, and then finish it off on this side of the fold. Great. And then what I'm going to do is have a look at the stratigraphy for the Silurian rocks, and I can see that there's just a relatively thin bed of limestone, just to give my rocks, just to give my section some degree of realism. Let's do that one in a fairly dark blue. And then beneath those rocks, let's just give that a very light blue shading. Okay, and then that's basically the subsurface of my geology done. There are some extra steps that we've done in this cross section, notably the Kink band method. But what we really did was to plot a series of dipping rocks that in one area of the map dip one direction and in another area of the map they dip another direction. Now I'm very confident that you guys can make cross sections like this, and I look forward to the point where we can get together and do them. But cracking on with this one now, what we need to do is then show off how our geology would continue up into the air prior to show what it would look like before the modern erosional processes. So what I can do is continue some of these rocks sensibly upwards, to show where they would be prior to modern erosional processes. And I always find that when I'm doing folded rocks, I always end up having to use a rubber because I'm apparently pretty poor at judging. Would end. So that's showing where our sandstone would continue. Then let's mark in these up to about there, up to about there, and so on. Yeah, that's more or less as sensible as I'm really willing to go at this point. Now, one thing that we might want to add on is our interpretation of where our fold hinge is, which I guess would, if we were to connect our fold hinges of our layers, it would go something like that. And then that's basically our section, our cross section done. If I would just label what this is as my fold axis. then we're pretty much there. At this point we can then go on to our good housekeeping measures and tidy this up and finish everything so that we get all of the information that we need. Okay, so now we can tidy up our cross section and do some of those good housekeeping measures that we need to be fully complete. Don't know what that is, but it's not going anywhere. Anyway, the first thing that we need to do is to give our map a scale. And just as we did with the Penrith sheet, all that we did was take the information that we've had on the map, transfer it onto one piece of paper, and then transfer that paper and that information onto a cross section. We haven't done any mathematical transformation, we haven't calculated anything for our numbers. Therefore, the scale of our cross section is the same as the scale of our map, which in our case is 1 to 50,000. Now if you wanted to, which is what we haven't done so far, we could also show a scale bar on our map to say that from a line 2 centimeters, from that distance to that distance on our cross section is 1 kilometer. I mean, as long as you know that 1 to 50,000 means every 2 centimeters equals 1 kilometer, I don't really mind which one you show, but it's kind of a good practice to have both, just in case anyone ever does what I've done and photocopies a piece of paper and then stretches it in some direction. Okay, so that's our scale, and then maybe what we need to show are some of these boxes, some of these rock types in a key. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 boxes. So we got 1, 2, 3, 4, 5, 6, 7, 8, 9, and let's just fit in another little guy there. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and then turn those into boxes. And starting with our oldest rocks first. So our light blue, and then our very dark blue, then we're going into our pink, then we've got our sandstone bed, and then we're into our St. Morgan's group. Then I've done my uppermost Devonian in a brown. All of my carboniferous limestones. I'm in danger of exhausting the blue area of my palette, but we'll see a workaround for that in a minute. Then our millstone grit, then leading into the pennant and the coal measures, Okay, then what I'm going to do is, because I've been a bit fast and loose with my labeling, I've grouped things and then decided to simplify things a little bit. I'm going to link all of these together, these bottom two to be my Silurian. Then all of these here, from the top of my brown to the base. Oh, that midpoint is slightly off. All of these are my Devonian. Then I'm into my carb limestone. And then I've got my millstone grit. And then these guys both belong to the coal measures. So these ones from here to here belong to, on our stratigraphic column, they're part of the upper coal measures. Okay, now at this point we could obviously give these rocks some labels, but I think it's fairly self-explanatory what we've got going on. The only other thing that I'd be tempted to include in this is to show where our unconformable horizons are. We've got this unconformity between the old red sandstone, or between within the upper Devonian. So we have a gap in geological time along here, which I'm going to try and mark on in green, like so. Where does that come down? We don't see it on that side. And then there's another unconformity between the limestone and the millstone grit. So we've got another one like so. And we can label these as unconformable contact. Okay, so looking at our cross section then, I think we can be pretty happy with it. We've got a realistic representation of our fold, which is true to the dips that we've recorded that are on the map. We haven't had to fudge anything. We've just shown how the dip could change from 25 degrees to 5 degrees on this limb of the fold. We've shown, we've kept our rocks as a constant stratigraphic thickness, and we've shown the different stratigraphic relationships between them. So I think we can count this as a success. We've plotted folded rocks, and we've learned a new method, the Kink method. And we've used this new method to give a realistic representation of the sort of stratigraphy we'd expect for sedimentary rocks. If you want to learn alternative ways to do this Kink method, there are a number of really useful online resources, a couple of blogs that give worked examples. And if re-watching this video doesn't help and I'm unable to help in person, then I'd recommend doing a bit of research for these other methods. But thanks for coming, guys. Stay safe and keep washing those hands. I'll see you next time.